We know there are three flavors of neutrinos: electron, muon, and tau neutrinos. But there are also three different mass neutrinos: nu1, nu2, and nu3, alternately referred to as mass 1, mass 2, and mass 3. Neutrinos are tricky, and it turns out that the mass and flavor neutrinos do not overlap perfectly. Each neutrino of a specific flavor is actually a combination of neutrinos of different masses. As a result, each neutrino of a specific mass has a certain chance of interacting as a particular flavor. For example, nu1 is very likely to interact as an electron neutrino. Scientists don't know whether nu3 is much heavier or much lighter than the other two mass state neutrinos. And if it is the lightest, it would be a big surprise. Neutrino physicists often talk about two scenarios for how neutrino mass might shake out. This ordering of neutrino masses is sometimes given the term hierarchy. In the normal mass ordering, nu1 is the lightest, nu2 is the middleweight, and the nu3 is the heaviest. This is called normal because it mirrors the masses of the particles that are associated with neutrinos. The electron neutrino is mostly made up of the neutrino mass state that is the lightest of the mass states. The other option is the inverted mass ordering, where the nu3 neutrino is the lightest. The electron neutrino is mostly made of one of the heavier neutrino mass states. Scientists can check whether neutrinos come in the normal or inverted mass ordering with experiments that look at how neutrinos change over long distances. If things are normal, certain neutrino oscillations should happen at a higher rate than in the inverted world. The probability that the neutrino flavor at the point of interaction is different from the flavor at the point of creation depends on the speeds at which the three mass neutrinos move. What scientists have not yet determined is whether the mass 3 neutrino is heavier or lighter than the other two. There are many possible grand unified theories, which seek to explain particle interactions as different manifestations of a single force, that predict the mass 3 neutrino is heavier than the other two. On the other hand, if the third mass state were lighter, a host of other theories about the nature of matter would become possible. In the end, scientists have to measure the ordering of the masses first, before they can use that information as a piece of the puzzle to learn more about the nature of matter and the universe. The definitive measurement likely won't come until the next generation of long baseline experiments, DUNE in the US and the Hyper-Kamiokande experiment in Japan.